So if we try to draw the very simple PV diagram from the real diesel cycle PV diagram that we can measure from the engine, we can see that, start from here, then compression and combustion or heat addition, expansion, and exhaust blowdown or heat rejection. Now we ignore intake and exhaust process strokes can be ignored. So that is how we can model a diesel cycle operation. So let me introduce the ideal diesel cycle. Okay, so the ideal diesel cycle should have 4 processes. So the first process is, again, because that is very ideal, the compression process, which should be very ideal. Means that your compression process should be isentropic or reversible adiabatic, which is the same as the SI engine or ideal Otto cycle. Then the next process is heat addition process, but in the diesel cycle case, your heat addition process should be constant pressure process. And the next process is expansion process, which is also ideal or isentropic. Then we have a heat rejection process, but even for the diesel engine, we should have exhaust blowdown. So the heat rejection process itself is exactly same as the ideal Otto cycle, which is constant volume heat rejection process. So we have 1, 2, 3, and 4. Now, based on these 4 processes of the ideal diesel cycle, can you draw the PV diagram and TS diagram? Okay, I'm going to show you directly without having you draw the PV diagram by yourself, but please do some practices to be able to draw PV diagram based on those 4 processes, even without me having to show you the next slide. So please pause this video and try to draw the PV diagram by yourself. Now, how does it look? So it looks like that, right? So it starts from 1, which is usually at the room temperature or slightly higher than room temperature, and basically the almost 1 atm. And now we have isentropic compression process that has 1, 2, 2. Okay. Then we have constant pressure heat addition, that is 2 to 3, and we have 3 to 4, that is isentropic expansion, and 4 to 1, that is constant volume heat rejection process. So that is how we draw the PV diagram for the diesel cycle. Now, W net, so net work by the diesel cycle can be also expressed graphically, as an area between, inside the closed loop of this diesel cycle. Okay, and now again, Q in comes into your engine from during 2 to 3, and heat rejection is in between 4 and 1. So by looking at this PV diagram, we have to point out that there are the key design parameters when you try to design the diesel cycle or diesel engine, or when you do the performance analysis of the diesel cycle. The first one is still, we have to think about the compression ratio. Okay. Now, because we removed the intake and exhaust process, your ideal diesel cycle also, that is closed system. Now, based on these all given conditions, the compression ratio is still defined in terms of the maximum volume to the minimum volume, or in the case V V1 or V2, right? And because mass doesn't change, we also can express the compression ratio in terms of passive volume V1 to this passive volume at V2. However, there is another the ratio that we have to think about when we deal with the diesel cycle, because during this combustion process, your volume also changes from 2 to 3. So the question is that how much volume expansion should happen during this combustion process? So that is another design parameter, and we call this as cut-off ratio. And we use R sub C, and that is defined based on V3 over V2. So these two ratios are the key design parameters of the diesel cycle, and we are going to revisit these two ratio values when you try to solve the example problem and so on. Okay. Now, as I said before, the net work should be also calculated for the ideal diesel cycle analysis, which is the first one that we always have to calculate. And from this energy balance analysis or first law of thermodynamics of the cycle itself, we already know that this net work can be calculated by Q in and Q out. Okay. So in the case, let me just use a capital letter instead of small letter as you see in the PV diagram. So don't worry about these small things. Okay. Now, or we can use the same equation in terms of everything per unit mass. So in the case, the unit is kilojoule per kilogram. Okay, that is kilojoule. But everything is, these two is per cycle. Don't forget this. Okay. Now, we also can calculate the net work by subtracting the heat rejection from heat input, right? And at the same time, the net work can be calculated by expansion work during the expansion process and minus compression work during the compression process. Okay? But when we see the diesel cycle, you have to be super careful when you try to calculate the expansion work, because now by looking at combustion process 2 to 3, there is also the volume expansion, meaning that during the combustion process, your engine also should do certain amount of work of expansion. And you have further expansion work during the process 3 and 4. Okay? So that is the key difference from the spark ignition engine, because in the spark ignition engine, your expansion work only has one term, which is due to the expansion process. But in the diesel cycle, you have two terms for expansion work. So now in the case, your expansion work is work done by this engine from 2 to 3 process, which is combustion process, and 3 to 4, that is expansion process. Now, let's try to compare two equations. Okay? Now, one equation is how we can calculate the net work by using Q in and Q out. Okay, so in order to be able to calculate the net work, you should know two terms. One is the amount of heat input, and the other one is the amount of heat output. Okay? But when you see the next term, next equation, in order to calculate net work, you have to calculate the expansion work or two works, right? And also you should have also compression work. So now we have to have 3 terms to calculate the net work. So 2 terms versus three terms. And obviously, no matter what equation you use, the net work should give us exactly same value. Okay, so that is totally up to you. Okay, and sometimes you have to do both. But if you really just directly are asked to calculate the net work, then I would use rather this one than the second equation. Okay, and now another thing we have to do for the thermodynamic analysis is the thermodynamic efficiency or thermal efficiency, which is still the same. You have to have net work divided by Q. So that is what we have to do. So always we have to know the net work and also thermal efficiency. Now, let's move on to the TS diagram. So can you really draw a TS diagram? Okay, so what is the difference in terms of TS diagram of the diesel cycle when compared to the TS diagram of the spark ignition engine or Otto cycle? And please try to make a good guess of how this TS diagram should look. And let me show you in the next slide. So now that is TS diagram of the ideal diesel cycle. Okay, so that is quite exaggerated TS diagram. Okay, but let's take a look. So from 1 to 2, we should have isentropic compression process, that is same the kind of constant entropy. And now from 2 to 3, that is constant pressure heat addition process. Okay. And I hope that you remember how to draw the constant pressure process in a TS diagram, okay, which is where the temperature should be proportional to the exponential S over Cp. So that is when P is constant. Now 3 to 4. So when you try to draw the plot, even though this TS diagram looks like it's kind of linear, right? But actually, I would rather draw, not linear, but more likely kind of exponential curvy. Okay. Again, this TS diagram is a little kind of exaggerated diagram, so you have to remember that. And now from 3 to 4, we also have constant entropy, and 4 to 1 we have constant volume heat rejection process, and this curve for the ideal gas with the constant specific heat, then that is basically proportional to S over Cv. So now because the Cv is always smaller than Cp, the slope of constant volume curve in TS diagram should be steeper than the constant pressure curve. So that is why we have different kind of slope for 4 to 1 process, which is steeper. Okay. And now again, your net work is still the area surrounded by the closed loop of this diesel cycle. Now we learned how we can draw the PV diagram and TS diagram, and how we understand each process, and how we can calculate the net work and the thermal efficiency for the ideal diesel cycle analysis. And let's try to use what we learned to solve certain specific example problem. Okay.